Hello friends, and welcome again to our e-mentoring for ee102. I'm Rajanath and I will be taking this session again. So previously we have looked at some applications such as superposition for, for the application of nodal and mesh analysis. Okay? So this week what we'll be looking at is source transformation, Thevenins. So these are the important topics as well that you need to know and understand. I believe that you have also had assignments on this, so take this as a review and see on what can be done. Okay, so source transformation is basically just the process of replacing voltage source that is in series with a resistor to a current source that is in parallel with the resistor. Okay, so if there is a source, meaning a supply, and the resistor, it is in series, you can actually change it to a current supply and a resistor. Okay, so you'll get to know this concept once we look at an example of this. Okay, so let's look at this example first. Okay, so it says that using source transformation, find V0 in the circle. Okay, so as you can see from the rules, okay. So first rule that we can see here is these two. Okay, so they are in they can be part of the rule. Okay, that the resistor and the current supply, they are in series, in parallel, so you can change these two, voltage and resistor in parallel, in series. Okay, so you can add these two resistors. Okay, so that is what we'll be looking at first. Alright, as you can see, so from previous example, how will we calculate the voltage? So we will do that by V is equal to IR. Okay, so we have a current which is 3, and we have our resistor is 4, so this gives us 12 volts. Okay, so the supply will be 12 volt and the resistor value will be the same, and that is what you will see here. Okay, so that is this part. This part and this part. Okay, so this 12 volt supply is the way it came as we discussed in the previous slide. You have to get that. Okay, so once you have that, as you can see, the 4 ohm resistor and the 2 ohm resistor, they are in parallel, in series. You can add them directly, which will give you 6 ohms. Okay, so 6 ohms is what you can see here. And 12. Now you can see that this side is already in parallel. So once you have done this calculation, probably you can make this side parallel as well. So current and resistor, so that you can add these two resistors, this one and the one that you will get parallel here, which will help you calculate. It will make this circuit actually more simple. Okay, that is what you can see here. Okay, so once that is done, then you can see that the 6 ohm resistor and the 3 ohm resistor, they are in parallel, so you can add them. Okay, and this current supply you have also got from the formula V is equal to IR. So this source transformation, it uses V is equal to IR mostly, and just your basic knowledge from how to transform from one form, which is voltage source in series with resistor, to current source parallel with the resistor or vice versa. Okay, so you can see once you add those two, you get 2 ohms, and as you can see, this direction of current is going downwards is 2, and this is going upwards is 4. So you add them, you get 2 upwards on this side. Okay, so 2 amps is going upwards, and you have this. Once you have this, this is like a simplified, most simplified circuit you can get for these two, or you can add. So this is an alternative, but then you can just use current divider rule. Okay, so in parallel we know that current divides, so the total current adds up to give the current. Okay, and in the current across these two resistors we add up to give 2 amps. Okay, so how will we know that? So you can use the current divider rule. Current divider rule is just basically if we are finding, let's say, I across resistor 1. Okay, so your formula will be R2 will be on top, the opposite resistor, upon R1 plus R2, R1 plus R2, and then we multiply this whole thing by the total current that is in the circuit. Okay, so this is known as the current divider rule. Okay, so in this case, since we are finding the current across the 8 ohm resistor, so the 2 ohm resistor will be on top, divided by 2 plus 8 into 2 amps, so this gives you as 0.4 amps. Once you have that, now you have the resistor, you have the current, you can easily find what is the voltage across the 8 ohm resistor, which is V0. So 8 times 0.4 will be 3.2 volts. So that is the answer that you get. So this is basically what two-part transformation is all about. It's just the basic understanding that you have learned in basic class on how to add parallel and series resistors, how to find total resistance, and then just switching it from one form to the other. Okay, from one source to the other. Okay, so we will look at another example just to see if we have really understood this. So this example is basically the same thing. The only difference here is just has an dependent source now attached to it, which indicates that that can be a bit confusing, but the concept is the same. Okay, if you follow the steps correctly, you should be able to do this. Okay, okay, so first of all, you can see that this, and this. Okay, so this is in series with the supply. This is a voltage. So you can change this into current in parallel with the resistor. That is what is being done here. Okay, so you get 3 amps as your current and 2 ohm resistor is in parallel with it. Once you have these two, you can see that this you can see this. Okay, so this is in parallel. This is still a current source. Okay, and it's in parallel with the resistor. So you can change that form as well. And that form comes down to something like this. So 4 times 0.25 Vx will give you Vx, because we are finding the voltage, and that is what we get. Okay, so once you have those two, so you add these two resistors in parallel, it will give you 1 ohm. It gives you 1 ohm, and now what you can do is you know that whatever value of Vx you will find here, okay, at this point will be the same value you will get across this branch. Okay, so now once you add these two, so you can just use the Kirchhoff's voltage law loop. Okay, so you go around the loop to get a general equation, but in that equation, if you know, you have two unknowns. You have Vx and you have I. You have two unknowns and you have only one equation. So what you can do is you can go back and do a Kirchhoff's voltage law loop only around this. Okay? Only around this branch. This will help you get a equation for Vx. Okay? So once you have an equation for Vx, then instead of having this Vx, you can actually achieve that in terms of I. Okay? So that is what we will be doing. So there will be an I here. Okay, I. Once you have this, then you want to see that Vx comes to 3 minus I. So this is what you will substitute here in place of Vx. Okay. So what you substitute equation 1 and equation 2, you get your answer as minus 4.5 amps. So minus 4.5 amps. Once you have 4.5 amps, then once you have this as answer, then note that we are still looking for Vx. Okay? What we will be doing here is Vx is 3 minus current value. Current value we found is minus 4.5. 3 minus 4.5 is equal to 7.5 volts. So just a quick review of this. Note that the circuit at first you can submit, let's say it's a bit tricky or it's a bit tough, but it's just basic understanding of this laws. Okay. If you understand your basic laws that you have learned in chapter and the beginning of towards the beginning of this course, then you should be able to do this. Okay. And note that in exams, if you are asked to solve questions using super transformation or source transformation, please use source transformation. If not, then you are heavily penalized. Okay. There can be instances where you also can get 0. Okay. So this is all for source transformation. Now we are looking at another application of it, which is Thevenin's. Okay. The Thevenin's demonstrates that a linear two-terminal circuit can be replaced by a conventional circuit consisting of a voltage source. In series with a resistor RTH. Okay? So the voltage source is known as VTH, which is Thevenin's, and RTH is known as Thevenin's resistance. Okay? So what this law means, and in this definition means, is you can have a big circuit. You can replace that circuit with an equivalent circuit using Thevenin's theorem, and replace that whole circuit with only VTH. Now, it's a base, some steps, and some rules that we have to follow in order to get that good. The first thing is we need to know the two cases, two types of rules that there. So first is if the network has no dependent source, so you just turn off all the independent sources, the only sources that are there, you can obtain your RTH. Okay? And case 2 states that if there is there are some dependent sources in the circuit, so you turn off all the independent source and you add a 1 volt resistor, 1 volt source supply or a current supply for 1 amp with the at terminals A and B. Okay? So in that way you're able to find the RTH and VTH. Okay? So that is what the circuit is talking basically explaining about, is turn off all dependent source and you calculate. Same thing we do here. Instead of just leaving this place open, you just either a 1 volt supply or 1 amp supply. Okay. Let's look at an example. Okay, so it says find the Thevenin equivalent circuit of the circuit below. To the left of the terminals AB, then find the current through the RL equals to 36 ohms. Okay. the first thing you have to see according to the case is whether there is any dependent source. So there is none. So what we will do in order to find RTH is we turn off all the sources. So that is what is being done here. As you can see at this point. Okay, so there is no more sources involved. So as you can see here is the 4 ohm and the 12 ohm are in parallel. And then those things just go in parallel. So and then these two are in series with the 1 ohm resistor. So you calculate and you get your RTH as 4 ohms. So this is still not done. Once you find your RTH, you have to find now your VTH. Okay. So how will we find our VTH? Okay. So as you can see, it's just the normal. You can use mesh analysis just to find VTH. Okay. Note that your VTH is usually wherever there is a point AB, okay, in the circuit. That will hint that that is where you have to find your Thevenin's voltage. So in this case, this is where our basic understanding comes in. VTH at this terminal, it is same in parallel with the VTH in across this branch. Okay, so as you can see here, this is where understanding comes that voltage is the same in parallel, and current is the same in series. So if we have to find the voltage across this terminal, this branch, it is the same across this 12 ohm resistor. Okay, so that is where we can find the voltage. If you find the voltage is this node, it will be the same as the VTH. So we go around the loop, you have two meshes, and then you rearrange your terms. Okay, and from the equation that you obtain, you should be able to get VTH as 30 volts. Okay, so this whole circuit is equivalent to only this part of using terminals. Okay. Now, the original question asked us to find the current across the 36 ohm resistor. Okay, so note that current is the same in series. Okay, so what we can do is we can just use V upon R to find current. So 30 volts is applied and we have two resistors in series, so we set them up. O plus RL and RL value is given as 36, so it's 30 upon 40, so it is 0.5 amps. So that is how you solve this question. Okay. So this is a pretty straightforward question. This was just to test your understanding. Okay. So note the first thing you have to find is RTH, and the second thing is VTH, after which you see what the question is asking you to find, what else the question is asking you to find. Okay, so in one case, it was to find IL across the 36 ohm resistor. Okay, moving on is the Norton's. Okay, so note that Norton's is pretty much similar to what we did for Thevenin's. Okay, the only difference here is the circuit. Okay, so for Thevenin's, we have to represent the equivalent circuit as a voltage supply, and the resistor was in series to the voltage supply. Okay. In Norton's, the difference between Thevenin's and Norton's is in Norton's, we will be using current source as a supply, and the resistor, the Rn, will be in parallel to it. Okay. So note that Thevenin and Norton's resistance are equal. Okay. So the only difference now will be to find Norton current. Okay. And Norton current is basically VTH upon RTH. Okay. So it's just like you're going a step further. That is what we are doing. Okay. We're just going a step further here. Okay. Let's just quickly look at this example and you will understand what we are talking about. Okay. So now as you can see here, this is a circuit which is find the Norton equivalent circuit of the circuit. Okay, so first thing is the way we used to find RTH, we find our RN. Okay, so we turn off all the sources, since there is no dependent source, we get this. Okay, we know that these three, the 8 ohm, 800 ohm, they are in series, but they are in parallel with the 5 ohm resistor. So we get a parameter as 4 ohms. Okay, find your your Norton current. You can use mesh analysis. Okay. If you use mesh analysis, you find your I1 and I2. Note that whatever your I2 value is, will be equal to your IN. Okay, and you solve it, and you should get that. And if we were to replace this circuit, how would we do it? Okay, so it would be something like this. We have the current source here. Okay, and then in parallel to that, you will have your RN resistor. Okay, and then you will have your points A and B. So in our case, this is given as 1 amp, and this is what we found is 4. So this is it. That's the answer. Okay, so I hope that this mentoring has helped you have a better understanding of source transformation, elements, and markers. Okay, thank you very much for your time today. Hope that this video